In lesson 7, we're going to look at systems of polynomial equations, and what this means is whenever you have two or more equations and you're looking at their solution. So the two types of systems that we're going to really focus on are quadratic linear systems and quadratic systems. But keep in mind that really you can take any type of polynomial equation and another polynomial equation and look at where their intersections are. So the first type that we'll really focus on is a quadratic linear system. And basically what happens is a quadratic linear system is whenever you have a quadratic equation, which means an x squared, and a linear equation, which just means a line, so just an x, and you look at where they cross or if they don't ever cross. So if you have no solution in a certain system, a certain quadratic linear system, that just means that you could have a scenario that looks like this, where you have a parabola and you have a line and they never cross. So they wouldn't have any points in common. One solution means that you have a line that crosses the parabola in exactly one spot. So the line's tangent to the parabola. So that would be the solution, or the point that they both have in common. And then two solutions is whenever you have a parabola and you have your line that's going through the parabola and it's crossing in two places. Now keep in mind that these three examples are just three examples. I could draw any type of parabola and any type of line and come up with alternate scenarios here. So here's another example of a system, a quadratic linear system that has two solutions. The next type of system that we'll look at is a quadratic system. So this just basically means now you're going to have two quadratic equations or two parabolas. So a first thing here is if we have no solution. So that means you'd have one parabola and you would have another parabola and they never cross. So they don't have any points in common. One solution means you have your parabolas have exactly 1 point in common. They cross in one spot. So something like that. Two solutions mean, again, your parabolas cross in two spots. So they have two solutions. And again, these are just some of the examples, some of the pictures that you would see. And then the last thing here, we won't really look at too much, but just so that you've seen a little bit, is remember we have polynomial equation systems. So basically any type of polynomial equation. So what if we have some even degree polynomial and we want to look at, well, what's its solutions with a line? So we would look at a linear equation and a even degree polynomial equation, and we're looking at, well, what points do they have in common? And if you looked at it graphically, it would be these 2 points according to my picture. You could also take some kind of cubic function and you could look at, well, when does that cross with a quadratic function? So when does it cross with this parabola? Well, there'd be two spots. So there's tons of different ways that you could look at this. So I could have another even degree polynomial, again with another even degree polynomial. And you could look at where's their intersection. So in this case, I have 4 different intersections, which means there'd be 4 different solutions to those two polynomial equations. So we're not going to go that in depth with that, but I just wanted you to at least see that systems extend to polynomial equations. Anytime you have 2 or more equations and you want to see where they intersect, you could go ahead and graph the polynomials and find their solutions by their intersection points. So let's just look at one example where we're actually going to go through and find the intersection points. And this is going to be a quadratic linear system. And I know that it's quadratic in a linear system because of the fact that in this first equation, I have an x squared, so that's going to be my quadratic part. And then I know that I have to have a line for the second equation because my x is to the first power. So this would be my linear part. So what I'm going to do is I'm going to number these, so equation 1 and equation 2, and I'm going to just go ahead and I'm going to graph these individually, and then we're just going to look where do they cross, and that'll tell us the point or points that these two equations have in common. So first thing we're going to do is let's graph this parabola. So thinking back to some prior lessons here, when we looked at graphing parabolas, we looked at some different things. The first thing was the leading coefficient test. So in this case, it's even degree and it's positive, so both ends are up. We looked at the zeros or the x-intercepts. So this is where you set your equation equal to 0 and solve. So I'd bring over that 2, take the square root of both sides. So this one I don't have to factor because it's just an x squared and a number. So I bring the 2 over, and you get x equals plus or minus. Now if you look, you have a negative underneath the square root, which means it's going to be an imaginary square root of 2. I basically pull out that negative 1. So what this means is these aren't going to be x-intercepts. So this does not cross the x-axis. So no x-intercepts is what this tells us, because remember, this is the real coordinate plane, the real number system coordinate plane. So we're basically, this whole step here really wasn't helpful because I can't really do anything with this plus or minus I radical 2. So you kind of just forget about that. And then let's move on to finding the vertex. So the vertex is my next step, because remember, the vertex is that point that's going to be in the middle. So in order to find the vertex, last time we looked at, well, if you find the zeros, like let's say I know that the zeros are between, or that the zeros were 0 and 2, I know that the vertex would have to occur at 1, because the vertex is always in between the two zeros. However, in this case, when you have these imaginary zeros, it's not as easy to figure out the vertex using those zeros. So what we're going to do instead is we're going to try to take this equation and we're going to get it into vertex form. So we're going to take this equation and we want to get it into vertex form. So vertex form, you can complete the square to get there. But in this case, vertex form, remember, is just when you have all of the x plus or minus some number, and then you have the plus number at the end here. So basically, to complete the square, I would bring over, so you could have brought over this 2, and then you could complete the square in x squared, but x squared is already a perfect square. So really what you can do is you can just think of this as x minus 0, because x squared is the same thing as saying quantity x minus 0 all squared. So this is in vertex form. So I don't really need to complete the square. You could complete the square, you'd get the same conclusion, but it's much quicker just to rewrite it like this. And then you see that the vertex has to be this number here, opposite sign, so 0, and then just the number at the end. So this is something that I can actually go ahead and plot. So 0, 2. Now you might also be thinking, well, the y-intercept is at 2, because the number at the end of my equation is the y-intercept, which in this case is 0, 2. So that doesn't really help me any. All I know is I have 0, 2. Now I know that that has to be the vertex, so that means everything else is going to be symmetric around this point. So now what I should do is I need to figure out some more points since I only know the vertex. So what I'm going to do is I'm going to find some more points. And basically, since I have my vertex, so I'm going to set up this table, and since my vertex is at 0, 2, that means all these other points are going to occur symmetric around this point. So what I want to do is I want to look at some x values, -1, -2, let's say 1 and 2, just basically so that this vertex is still in the middle, because we want symmetry to occur. So what I'm going to do is I'm going to figure out, well, what's the point when x equals -1? So let's say x equals -1, we want to find y. So basically what that means is you're going to plug in -1. So we get 1 plus 2 gives me 3. Which also tells me, so if you go up here and you plot -1, 3, that also means that at x equals 1, the y value has to be 3, because these have to be symmetric. So if you have your vertexes in the middle and one away on the left is up at 3, the one away at the right has to be at 3. So basically, as soon as I figure out one of these, I know that the other one has to be 3. Same thing goes with the negative 2. So let's say I say x equals negative 2 and I plug that in. So y equals negative 2 squared plus 2. So I'm just plugging them into my equation. So 4 plus 2 gives me 6. Well, I know both of these have to be 6. So I can go up here and I can say, well, if negative 2 is 6, then at positive 2 has to be 6, because 2 units to the left is up at 6, 2 units to the right of the vertex also has to be at 6. So now we can go ahead and we can connect our parabola now that we have enough points. And we're going to go ahead and label this. And now we're going to look at graphing the line. So now the second step is going to be graph that line. So 2x minus y equals negative 2. And we know that whenever we graph a line, we have to get our equation into y equals mx plus b form. So I'm going to subtract over the 2x. And again, I'm putting this in y equals mx plus b form, which is why I have my x first. Then I need to get y by itself, so divide everything by negative 1. So we get y equals 2x plus 2. So then my slope is going to be 2 over 1, which means up 2 because it's positive and we always go to the right. Y-intercept is 2, where my starting point is at 2. So I'm going to start at 2 and I'm going to rise to right 1. So start at 2 and you're going to go up 2, right 1. Up 2, right 1. Up 2, right 1. Up 2, right 1. And then you're going to backtrack. You're going to go the opposite direction. Down 2, left 1. Down 2, left 1. And once you get all of your points plotted, then you can take a straight edge and you can connect these. And you should be seeing that your graph is actually crossing your parabola, or your line is actually crossing your parabola in exactly 2 places. So here's my equation, my line. So we have 2 solutions. We have one right here and one right here. So all we need to do now is just state those solutions. So we have 0, 2 as a solution, and we have 2, 6. And now to actually check that those are solutions, what you could do is you could take each of those and plug them into both equations. They do have to work into both equations because we're saying that those are the points that are in common for each equation. Otherwise, you could, if you had the ability to use a graphing calculator, you could check your graphs in a calculator. You could also check the system algebraically, which is what we're going to look at in the next lesson. But always make sure that you state your solutions before finishing up the problem.